Hello, everyone. Welcome to lecture number 27, where I'm going to begin a discussion of magnetism. Okay, we discussed electricity, and electricity and magnetism are intimately related. There's no math in this part, so there's a lot of hand waving, a lot of explanations. So try to take notes or read the book or go to YouTube for great lectures or Khan Academy. Okay, but again, there's no math, right? We're going to talk about magnets and no magnetic monopoles. If you'll recall, and students do this all the time, they mix up electricity and magnets, okay? So remember, if we had a plus charge and we had a minus charge, we said the plus charge is a source of electric field, right? And the negative charge was a sink. And so our field lines due to Faraday looks something like this, right? I could draw a lot of lines, arrows going from the plus to the minus. These are electric charges, okay? Magnets, as you know, I'll draw a bar magnet, a standard uh, magnet. Well, for magnets, we no longer talk about plus and minus. We talk about a north pole and a south pole. The north pole would be equivalent to a positive pole because we're going to see that the field lines emanate out of it. Okay, so I'm going to put a south here and I'm going to put a north here. Right, this is a bar magnet, nice magnet. This is called a dipole. Why is it a dipole? Because there's two poles. Okay, and here I'm going to draw another magnet. Here I'll put a south and I'll put a north. Okay. Our rule that opposites attract holds also for magnetism. So a north pole and a south pole will attract, two north poles will repel, and two south poles will repel. Okay? Same type of picture. All right, so we imagine, again, due to Faraday, we use our imagination, these magnetic field lines. Remember here, these are electric field lines. Electric field lines. Now we're going to imagine magnetic field lines coming out of the north. And what they're going to do is they're going to go in to the south. Okay, so this would be our picture for attraction. And these things would still come out and actually circle back to here. You see that? And these lines would come out and circle into there. Okay? It looks like a sports football play. So the field lines come out of a north and into a south. So the north would be a source, the south poles would be a sink. If I had two north poles, again, the lines come out, but now they repel. Two north poles, they repel, the lines repel. Okay, if they were two south poles together, same picture, but the arrows would go in. Remember, south poles are sinks. Okay, so north and south poles, and here we have electric charges, plus and minus. Do not confuse them. Okay? All right. Now, I have a word about monopoles. I said that a bar magnet was a dipole, two poles. We said an example of electric monopole, monopole. Monopole means by itself. Well, a positive one would be a proton. A negative, an example, would be an electron. But what about a magnetic monopole? Monopole. That's good. Okay, what about a magnetic pole? Well, that would mean you just have a north pole or you just have a south pole by itself. And it turns out that we've never seen, whether they exist or not, we don't know. We've never seen a magnetic monopole, a north pole by itself or a south pole by itself. They come in dipoles or higher poles, quadrupoles, octopoles, never a magnetic monopole. So magnetic monopoles do not exist as far as we know. So that's a tricky question, right? Electric monopoles exist, but magnetic monopoles always come in pairs. Okay, so you could have a dipole. So a bar magnet is a magnetic dipole. Okay. Law of nature number one. I'm going to talk about two laws of nature in this magnetism part, okay? Here's one law of nature. Moving electric charges produce magnetic fields. And I put the question, why? Nobody knows why. This is the way our universe is, but it's a fact that if you take an electric charge, you produce a magnetic field. So let me show you a silly little picture, okay? So let's suppose we have a proton. Remember, there's electric force field coming out. This is electric field. I'm only drawing a couple lines. Remember, it's a source of electric field. The field lines are emanating out of the proton or a positive charge, whatever it is. If this charge is stationary, we say this is a static charge. Nothing's happening. Static. Now imagine, again, use your imagination, all right? Try to imagine these electric field lines as strings or jump ropes. Okay? Now, suppose I take this charge and I wiggle it up and down. What happens when you take a rope and you wiggle it? When you wiggle it, you get wiggles in the rope. And you get wiggles and wiggles. So I'm going to wiggle this charge. Now, I say wiggle. You want to get fancy, you could say oscillate or just move it. It doesn't matter. I'm just going to wiggle it, okay? Not that fancy. When you wiggle this, what happens to these electric field lines, like a rope, is they wiggle. So now I'm going to draw this line just here. I'm going to say as I wiggle it, okay? So this represents a wiggling electric field. Wiggling electric field. I'm going to call that WEF. What is WEF? Wiggling electric field. Okay? So this is my wiggling electric field. Remember, when it was stationary, that's a static electric field. Now, when I wiggle it, notice you see these little bumps? These bumps or kinks. These kinks in the electric field are actually, this is what we're producing, actually magnetic fields. Not only are they magnetic fields, so these kinks, remember you don't have kinks or wiggles, you don't have these little bumps or kinks unless you wiggle, right? When these are straight, there's no kinks. When I wiggle this, I produce these kinks. These kinks are actually magnetic fields, but watch this. They're actually wiggling magnetic fields. WMF, wiggling magnetic fields. So these wiggling electric fields, all these kinks, are producing wiggling magnetic fields. Now notice, this gets crazy, these wiggling magnetic fields have kinks in them, or bumps. What are the kinks in the wiggling magnetic field? These kinks are just wiggling electric fields. Wow, isn't this crazy? So I'm going to erase over here and summarize. Okay, so watch. If we take an electric field with an electric charge and we wiggle it, what we're saying is that wiggling electric fields produce what? Wiggling magnetic fields, right? But now we have wiggling magnetic fields, and we just said that wiggling magnetic fields produce what? Wiggling electric fields. But wiggling electric fields produce wiggling magnetic fields. So together, we have wiggling electric fields and wiggling magnetic fields. So wiggling magnetic fields plus wiggling electric fields together, we get wiggling electric and magnetic fields. And this, when you have electric and magnetic fields together, this is called electromagnetic radiation. Electromagnetic radiation. I will have a lot more to say about this, okay? But rule number one, law of nature number one, moving or wiggling or oscillating electric charges produce wiggling or moving or oscillating magnetic fields. But moving, wiggling, oscillating magnetic fields also produce moving, wiggling, or oscillating electric fields. And together, they're called electromagnetic radiation. So if we imagine the wires going through the wall or going through the ceiling, there's moving electric charges, and guess what they're producing? They're also producing magnetic fields that are wiggling or oscillating. Okay, so that's electromagnetic radiation. I will come back to that. We have a lot to talk about with that. All right, again, no math, just a lot of words. Law of nature number two. All magnetic fields are produced by moving electric charges. All magnetic fields are produced by moving electric charges. Well, that's kind of curious, because I want to show you or explain, again, hand wave and try to explain in very simple terms. How could I have a bar magnet? Remember what a bar magnet is? That's just a thing you buy in a store. It has a north pole and a south pole. Remember, the field comes out of the north, circles back to the south, but it's just sitting there. There's a magnetic field. I just said that all magnetic fields are produced by moving electric charges. I don't see anything moving here. Do you? It's sitting there. All right, so let's go to a microscopic level and talk about what's going on. Okay? We're going to go back to our naive picture of the atom as a tiny solar system. Whose model was that? Remember Bohr, the Bohr model of the atom? Tiny solar system. So let's look. Suppose we have a proton or we have a nucleus. I don't care what the charge is. And we're imagining that we have an electron going around. Okay? Remember, electron going around is centripetal motion. Remember that? Going around the circle, centripetal acceleration, etc. All right, let's talk. We just said that all moving charges produce magnetic fields. So if this electron is going around, and let's just say this is hydrogen. One proton, one electron, a hydrogen atom. Electrically neutral. If the electron is moving, not only does it have an electric field, but it has a magnetic field. Okay? It's not important to know what direction, but I'm going to tell you. There's a right-hand rule. Actually, it's negative. It should go the other way, but it doesn't matter. It turns out that this atom, because this electron's moving, is going to make a little magnetic field. Okay. What would happen if I had two electrons? So, for example, in helium, helium's the second element on the periodic table, has two protons and two electrons. Once again, electrically neutral. If you have two electrons, the question is, does that electron go in the same direction or does it go in the opposite direction? It's a good question. I'm going to answer it. I'm going to answer it with this statement that I wrote up here. All things in nature want to be in their lowest energy state. Okay? So let's talk about an electron going around. Suppose a particle is going around this way. If you take your hand and you curl it in the direction of motion of the charge, okay, again, I'm off by a minus sign. It's not important that it's negative. If you take your hand and put it in the direction of the charge moving, because it's really electric current, you'll get your thumb makes an arrow. That's the direction of the magnetic field. So now suppose you have two electrons going in the same direction. So what you have now is two arrows going up. So you have twice the magnetic field if the two electrons go in the same direction. Well, what happens if one electron goes one way, make an electric field, a magnetic field, and the other electron goes the other way? Then I get a magnetic field like this. The total magnetic field is 0. Same direction, you get 2 times the magnetic field. Opposite directions, you get 0 magnetic field. What would nature prefer? Well, nature prefers the lowest energy state. So what's a lower energy state? Twice the magnetic field or 0 magnetic field? The answer is 0 magnetic field. So if you have 2 electrons, the atom has 0 magnetic field. Cool. What if it had 40 electrons? What would the net magnetic field of this atom be? The answer is 0. Why? Because 20 would go in one direction and 20 would go in the other direction. What if it had 130 electrons? Well, 65 would go in one direction, 65 would go in the other direction. Okay? Again, an even number. But if the atom had 21 electrons, 10 would go in one direction, 10 in the other. One electron would be unpaired, right? So if you have an odd number of electrons, that atom would have a magnetic field. Okay? If you have an even number of electrons, no magnetic field. An odd number of electrons, you have a magnetic field. So let's look at a magnet. Here's my magnet. Each atom, let's imagine we have each atom. Here's my magnet. And let's just suppose that each atom has an odd number of electrons. That means each atom has its own little magnetic field. So I'm just going to draw a bunch of atoms, okay? These represent atoms, okay? Once again, it's supposed to be a three-dimensional motif, three-dimensional array. And each atom, if there's an odd number of electrons, each atom has a magnetic field. So this guy has a magnetic field that way. This one has that way. This one has this way. That one that way. I don't know. They're all completely random. Each atom has their own magnetic field. So the question is, what is the total magnetic field of this system? Forget bar magnet. Just say it's some system. So what's the total magnetic field? Well, even though each atom has an odd number of electrons, has its own magnetic field, since it's completely random, when you add up the total, on average, anytime there's a magnetic field going that way, because it's random, there should be one going in the opposite direction. So the total magnetic field for this system should have zero magnetic field. And that's even with an odd number of electrons. If there was an even number of electrons on each atom, of course, there's 0 magnetic field because each atom wouldn't have a magnetic field. So the total of all these zeros would be 0. So the question is, how does a magnet have a magnetic field? How could a magnet have a magnetic field? Okay. Well, again, if we look at a bar magnet, so let's suppose this system is a magnet. In a magnet, let me draw it here again. In a magnet, if I put north here and south here, we said the magnetic field goes like this, right? It's coming out and going into the south. How could a magnet, a permanent magnet, have a magnetic field? Well, what happens is the lowest energy state in this system is that this guy's magnetic field and this guy's magnetic field and this guy's magnetic field and this guy's and all the little magnetic fields line up. All right, sometimes there's a wise guy, but in general, they all line up. Why do they line up? It's a great question. In very few systems, by lining up, that's a lower energy state than being random. In most systems, the lowest energy state is to have the magnetic fields completely random, so the system is not magnetic. You see, if all these guys pretty much line up, then I have the magnetic field coming out. So this would be north, and this would be south. Where did these magnetic fields come from? They came from moving electric charges, right? The charges are moving around, producing magnetic fields. So the question is, are most things in nature magnetic? So if I took a magnet and I walked all around campus, all around the city, all around the world, and I tried to stick it to things, would a magnet stick to most things? And the answer is no. Trees, cement, buildings, ground. Most things are not magnetic. What does that mean? It means the lowest energy state of most things is to have zero magnetic field. How does a system have zero magnetic field? Well, again, two ways. Each constituent atom or molecule, right, has an even number of electrons. If it has an even number of electrons, this atom or constituent has zero magnetic field. This constituent has zero magnetic field. When you add up all the zeros, the total system has zero magnetic field. If, however, this constituent or atom or molecule or ion has an odd number of electrons, it has a magnetic field, and this guy has a magnetic field, and each one has a magnetic field. But the lowest energy state for most systems is that every magnetic field is random. So when you add the total, every time there's a magnetic field in the system going that way, there's one going that way. When you add it up, the total magnetic field is zero. So most things in nature have zero magnetic field. Why? Because everything wants to be in its lowest energy state, like you do right after this lecture. Go have a nice glass of wine and sit on the couch and go to your lowest energy state. So only very few special systems is the lowest energy state such that the individual magnetic fields line up. And that's what a bar magnet, a permanent magnet is. And I just wanted to tell you very quickly, if you add heat to a magnet where the magnetic fields are all lined up, if you add heat, remember adding heat is giving energy, which means the kinetic energy increases. It means these little magnets inside, these little atoms start to wiggle, and what you can do is then make all the things random. And so what happens if you heat a magnet, you can make it become unmagnetized, because instead of everything lining up, by adding energy, you break that alignment and it becomes unmagnetized. If you don't heat it too much, and that temperature is called the Curie, after Madame Curie, the Curie temperature. As the system then cools, everything then hopefully will go back to its lowest energy state, and then the magnet will become magnetized again, because everything would line up. But when it's heated up, all the little magnetic fields are random, and the average magnetic field is zero. So I think we covered everything that I wanted to cover in this first lecture on magnetism. Why are most things in nature not magnetic? Lowest energy state. All magnetic fields come from moving electric charges, or wiggling electric charges, or oscillating electric charges, if you want to get real fancy. And when you wiggle an electric charge, you produce a wiggling magnetic field. But a wiggling magnetic field produces a wiggling electric field. And together, that's a wiggling electromagnetic field. Okay, we'll talk about electromagnetic radiation. By the same token, if I take this magnet and sit it here, there's a static magnetic field. If I wiggle this magnet, I'm making a wiggling magnetic field in space, but that's producing a wiggling electric field. So I am producing a wiggling electromagnetic field, or electromagnetic radiation. So radiation is all around us, and in the next lecture, I think I'll talk a bit about the electromagnetic spectrum. All right, have a great one. Peace, be well, be safe.